I mean, yeah, I often feel like I'm calling out things where I'm like, I can see Benjamin's face right now, and he did not fully pass the last thing that was just said. Um, so yeah, that's totally fine.
Yeah,
And
Benjamin's
also,
breaking. His eyes doing that thing. We should slow before we blow a gasket.
I mean, this is why I try to encourage people to watch the episodes, not just listen to them, because your facial expressions, for me, are the favorite part of recording.
Oh man, this is pretty much it. Howard, you just sit there and you just watch Kovi and I just speak lovingly to each other, and you just read a book,
Easy.
grab yourself a coffee, something.
I can handle that.
Welcome to another episode of The Nerd and the Scientist, everybody. Today, our guest is an astronomer from UC Berkeley named Howard Isaacson. Works with or researches exoplanets, black holes, nearby stars, and mentored my nephew, Mr. Adam Zabridger. So, two questions. Let's just start us off. It's written that you research nearby stars. What's the cutoff? Where do the nearby stars stop, and when do the faraway stars begin? And Adam, right? He's real good. He's a good boy.
Adam's great. Well, first of all, thanks for having me. Really appreciate you guys. Happy to chat with you. No, Adam was great. Happy to be connected with you through him, and it's always a pleasure working with the students here at UC Berkeley. They're just way smarter than I was when I was their age, which is always impressive to me. Awesome. And they bring new life to my perspective. Right? It's like I get bored with things, and they make me realize that they're actually really exciting things. So that's great. Nearby stars. So it's a good question. So distances and brightnesses in astronomy are completely relative depending on who you're talking to, right? Nearby stars, for some people are, the nearest by stars, like the 10 closest stars. And if you talk to people who study stars in the center of the galaxy, it's like, nearby, like 1,000 light years away, nearby, very nearby. I'm like, okay. For me, I consider nearby stars about 100 light years away. So it's like sort of a circle going out from the Earth, 100 light years in all directions. And some of those are stars you can see with your naked eye. A lot of those stars are the brightest ones, so they're much further away. But yeah, 100 light years, I'd say.
About how many stars are in that 100 light year bubble?
Yeah, good question. So one of the newest missions that the European Space Agency put out, the Gaia space mission, they measured everything out to 100 parsecs, so about 300 light years. And they found about 100,000 stars. So then 3 times that distance, we can call that nearby, about 100,000 stars. Sorry, 100,000 stars. I think that's right.
It's amazing how far us radio astronomers are lagging behind, like the most recent catalogs of all of the stars that we've detected with radio telescopes is like barely 1,000 stars. We know that there are more out there, but just we're just not getting them. So I'm curious, how did you end up, I know that you have kind of like a non-traditional path. How did you end up in astronomy, and then how did you end up working on the stars?
Yeah. So I think a traditional path in astronomy is sort of people do undergraduate college, they do graduate school, get a postdoc, researcher, faculty. It's a really common path for people. So I did an undergraduate program. Took a year off from school, started a graduate program just to do a master's program rather than a PhD, which is the normal path. Both of those happened at San Francisco State University here in the Bay Area in California. And then I went to work directly after I got a master's degree directly here at UC Berkeley, supporting a ground-based observing campaign that was in support of the Kepler Space Telescope mission. So working around most people who already had PhDs or are on their way to getting a PhD. And I didn't start a PhD campaign of my own until about 2019. And I started it at the University of Southern Queensland in a program where they emphasize remote learning. And so I could do all the work I was doing here, plus more work to get the PhD. And I finished that last year to get a PhD to kind of get to the same level as sort of most people have when they start doing professional research. That's the real short version, I guess.
I love the wackadoo routes everyone takes to get to where they are in their science. There's no linear anything. It's just beautiful.
Yeah, I feel like non-traditional paths are the new traditional paths. Like at this point, I feel like, and it's so great that there are remote frameworks or asynchronous frameworks that allow people to, you know, prioritize what they want to prioritize in their learning. That's so cool. So how did that work with like being part of an Australian university? As you probably can tell by my accent, me too.
Yeah.
Without physically being there, did you get a chance to visit? What was that relationship like?
Yeah, it was mostly through the sort of COVID era, and so I didn't have as many opportunities to visit as I would have liked. But I had a really great visit sort of the year before I finished up. For the most part, it was bi-weekly, twice monthly meetings with Brad Carter, who's a professor at USQ, and another one of my mentors, Stephen King, who's at UC Riverside. He's originally Australian, works in California now, so he also was an advisor on the program. So I met up with those guys, and some days I would come in, I'd be like, I have all this progress. Let me show you all the things that I've done. And they said, great, keep going. You're doing great. Keep going. And other days I would come in and I'd be like, well, I didn't really make any progress because of a million reasons that, some having to do with work, some not. And they'd be like, great, keep going. Just keep going. Keep pushing on it. Same response every time. Just very encouraging. Really just on my side for all the things that I was going through in my own head about astronomy and everything else in that time period. And eventually slowly those ideas turned into papers. The first paper came out and it was sort of a nice sort of monkey off my back. This was after sort of 3.5 years of working in the program. And then in the last year and a half, things really came together. I took a visit down to Brisbane. I visited USQ and the two campuses, Springfield and Toowoomba there, and a couple other places as well. Everyone was just really gracious, as getting rides to all the different universities, and people want to talk. I gave several talks about the research I was doing, and just giving those talks and having a chance to get people to interact with the work that I was doing and to ask questions, and just the preparation itself for giving the discussions really kind of jump started me for that last push of finishing the second paper that was halfway done and writing the third paper right after that to just finish up. So it was a higher degree by research. I wasn't required to do the classwork, so that was something that I took care of in my own master's program at SF State. So I didn't have to repeat that. And that made the time change and the communication with Australia much easier, because that time change is wackadoo.
Mm-hmm.
Yeah, Benjamin has to deal with it.
We have that problem scheduling sometimes our recordings, given I'm in San Francisco Bay Area and he's in Sydney. And
it's like next Tuesday, right? In Sydney right now, isn't it?
Tuesday. I think it's February Tuesday at the moment.
February, yeah. That sounds right.
It's hard to tell when there's a whole planet in the way. I love that joke. I love that we have that joke.
But to summarize, the program was really great. I was really, really appreciative of all the effort and time that was given to me from Brad Carter and Stephen Kane and other people. And I've recommended it to several other people in the Bay Area, and they've already pursued that same degree at USQ.
Cool.
Yeah,
that's really cool.
That's what I should do.
I mean, they would have to change the name of the show, right? It would just be the nerds and the scientists. Or just the scientist and the scientist.
Okay. I'll keep myself where I am then. I know my place. So how many tell us about searching for exoplanets. How many have you found? What was is there one that's been tricky and evasive that you knew was there and then you found it somehow? What's the process like?
Yeah, it's one of my favorite things about astronomy is this process. And so I'll take a minute to give a little bit of background on how I got started in that question in particular, which is literally reading Discover magazine when I was in high school and being amazed at these discoveries, the high school physics project on exoplanets and center of mass. Went to SF State looking for a professor to do research with who wasn't there anymore. He's totally gone. And got really fortunate that another professor came along doing exoplanet research, and her name was Deborah Fisher. She was an excellent mentor, amazing scientist, and I got to start working with her. I started collecting data, which was really the thing I wanted to do the most. I thought the idea of like going to the top of a mountain, sitting up all night in the dark and collecting photons individually was like the most romantic thing in the world. It was
Totally.
a while ago, so it was like a little bit more remote now than it was then, right? I didn't have a cell phone. It's like you didn't like watch YouTube all night. Like it really felt like it was something happening when no one was paying attention. And that was sort of that was in my undergraduate career. And the thing I really wanted to do, because I wanted to really do observing, I got to do a lot of it because not everyone wants to. So I got a lot of opportunity to do that. And I picked up a lot of skills in terms of how you collect data the best and the best methods, using the best practices. We're trying to measure these incredibly tiny changes in the positions of the spectral lines of these stars. That's how we measure the gravitational interaction between planets and stars. Think of like the pixels in your cell phone camera. We're trying to measure 1/1000th of a pixel changes with these measurements. So it's incredibly tedious, and the hardware is as interesting as the software. And when you're at the telescope, you get to walk the light path. You see all the different optics that the light is bouncing off of. A shell spectra is sort of the main optic we use in our field. But you also get to see the primary mirror, right? The primary mirror of the Lick Shane 3-meter telescope, where I started doing observing, is 3 meters, right? It's a huge piece of glass. It's in a dome that's 3 stories tall. It goes back to that sort of romanticism that I thought was just amazing. You hear all the gears moving. You see this monster thing going all in the dark, all on its own. And I just thought that was really great. So all the observing skills that I picked up in that undergraduate time, and then I had the same mentor as a graduate student at SF State, really set me up for doing that same type of work here at UC Berkeley, where there was a huge campaign that was about to start for the Kepler Space Telescope. So I was about to finish my master's degree. Kepler launched in March. I got hired in January. I was fingers crossed for not exploding on the launch pad. That happens sometimes. It didn't. Everything went up without a hitch. I started in June. My first day at the office was at the telescope. Sort of an era change. We started doing all the observing here at UC Berkeley in a remote observing room. So it wasn't already, that sort of romanticism had already been worn off after a few years of having done it. They were already changing, and now it's very, very much remote almost all the time. But yeah, the very first day before I had an office key, I had a key to the remote observing room and started doing that. In support of the Kepler space mission, we had some amazing discoveries, which I'm happy to highlight some after I finished, saying that over the time that I started here at UC Berkeley and sort of the first 10 years, I did about 400 nights on the Keck telescope in Hawaii in support of exoplanet discoveries, with many other people who did, just as many nights, and over thousands of nights over that time period, we made some really amazing discoveries. I'm happy to highlight some of those if you guys want to hear about some of my favorite discoveries. I think you asked about.
Absolutely.
So one really fun thing about being at the telescope and involved in a mission like the NASA Kepler mission is that you are just like right in the middle of it, right? You're in the kitchen when the chef is making the sauce, right? You're the editor of the book that hasn't been released yet, and you've got an advanced copy. So we're like, looking at images come right off the telescope, and someone's sending an email like, did you get that image yet? Did you get that image yet? What's going on? Like, do we know yet? Do we know? We have this exotic top thing. We got to figure it out. And, that sort of real-time excitement was great. There was, this wasn't exoplanet discovery, but it was a exciting Kepler discovery. They have these stars that were discovered with Kepler called heartbeat stars. They're a binary star system, so 2 stars going around each other. The very first one they found was a binary star where the 2 components were almost exactly the same mass. So they're really hard to disentangle their spectral features, which is what we do with the observing that I did, high resolution spectroscopy. And this light curve pattern that was coming from Kepler, that's what Kepler really did well. It took brightnesses of stars over time, very continuously, almost no interruptions, very, very precisely. And so these heartbeat stars had this sort of what you see on an EKG. It's just like, like a blip and then a pause and a blip and a star in a very periodic manner that's related to the period of the 2 stars going around each other. And we would take these spectra a couple nights apart, and they would be completely different. And it wasn't until we had like the 3rd or 4th one, and we're looking just like fresh off the telescope, and it was like, this is a binary. They're exactly the same. It's not 3 or 4 stars. It's not just 1 star. It's not a pulsation star. It's this really interesting binary scenario, and like fleshing that out in real time was really a fun part of observing. 2 more highlights I think are worth mentioning. One was the very first rocky planet that we confirmed the mass of. So Kepler was able to find transiting planets. So it was able to measure the size of the planet relative to the size of the star. And that told you, if it's a planet that's 1 times the size of the Earth, or 4 times, or 10 times. Jupiter's about 10 times the radius of the Earth. So we're getting down with this really precise Kepler photometry to the sort of 1 and 2 Earth radius planet. Never really been seen before. And the goal that we're doing with this follow-up observing is to measure the mass. Kepler gives you the radius, we measure the mass, then you have a measurement of the density, just the mass over the volume. And basically what you can figure out is if it's some low mass object like consists of something consistent with water, like Jupiter and Saturn, very low density, or something that's definitely rocky, right? Mercury, Mars, Venus, and Earth. And as these measurements came in, you're just hoping for clear weather every time. You're taking, 20 times longer than we used to take for the brightest stars, those nearby stars that we talked about earlier. So every observation is really painstaking and sensitive. And, that came out on, the result of that was Kepler 10b, the first rocky planet. It's in a less than 1 day orbital period. But to see sort of the data come from Kepler, the follow-up observing a month later, the initial interpretation a month after that, the paper, and then in the New York Times a couple months later to see like every step of that, and the New York Times being sort of the pinnacle of what you hope for in your science discoveries, right? It's like when you get there and it's condensed into 500 words, you're like, wow, that was a lot of work for those 500 words. But, glad everyone knows about that.
New York Times is like, that's it? That's the tippy top of getting your science work out there? Really?
Yeah, I think so, yeah.
That's hysterical. Love it.
There are plenty of great discoveries that don't get there, but I think that's a really good metric for how widespread the discovery is. Yeah. And
do you feel like? Oh, sorry, go on.
I was just going to mention a couple other discoveries that I think are pretty interesting. Do you have a follow-up question to that one, or?
I was just going to ask how you felt, whether there was any difference between the way that outlets like the New York Times were able to really capture the most interesting part of the story scientifically versus the most interesting part of the story from a consumer level, if that makes sense.
I mean, yeah, the end result of scientifically of what you get out of it is like the mass and density of the planet. It's a rocky planet. It's a headline that you can they totally were effective at doing that. But to condense it so briefly into something that I know took so much work, even on my own, I think it was the hard part to make the connection. I was like, man, I mean, yeah, they got the word out there and they got their point across, and it's accurate, 100% accurate, but doesn't really convey the amount of money and effort and time that goes into those kinds of things.
Fair enough.
I never really thought about
Blood, sweat, and tears.
That's a serious point.
But yeah, I mean, I could go
I don't
on.
want to keep you from listing your other discoveries that you wanted to share. Please continue. These are great.
Kepler was the most amazing thing. So before Kepler, there had never been a planetary system with more than one planet that was found by transits. So multi-planet transiting systems. And it wasn't like, we found, the most interesting thing that came out of it in a population level is that we were looking for things that were kind of like the solar system, some rocky planets, some further out gaseous planets. And instead we found all these planets really, really closer in than even Mercury in our system. Almost every star has them. And they're between sort of the size of the Earth and the size of Neptune. We call them super Earths because they're a little bigger than Earth, and mini Neptunes because we don't have anything that's like, they're not just like planet XYZ. We don't have that. They're just right in between the planets we do have. And they're just all over the place. I mean, if you do like accounting statistics and you say, for every 10 planets, how many planets are there of all these different sizes? And it's like one. Like one for every planet, for every star. That was kind of the new joke going around. It's like just the prolific nature of these planets was a huge Kepler discovery. But in terms of individual systems, we started to find things like Kepler 11 system that had 6 transiting planets, and they're not just sort of doing their own thing where there's some rocky ones and some gaseous ones. They're all pretty similar in size, and they're all really close together in their orbital spacing. And so when that happens, you get gravitational interactions. And we have those in the solar system, but to a much smaller extent, because these planets are close and because they're close in mass and radius as well. They have these interactions you can measure with the Kepler photometry. They call them transit timing variations. And it's exactly what it sounds like. Instead of having strict periodicity, because they're orbiting their star in a gravitational orbit, they're pulled a little bit ahead sometimes by that next outer planet, or they're dragged behind a little bit when we expect them to transit by that planet. And by getting these patterns over this sort of 3 and 4 year timescales, as the data volume grew, they're able to find the exact masses of the planets of this entire set of planets, 1 out to planet 6. And it was just incredible to have the knowledge of these really small planets in this really tight configuration, and all the masses are completely known. Completely unprecedented discovery in exoplanets. That was a really good one.
From all that pulling and pushing of the planets that are in that little assortment of planets, are they like literally speeding up, slowing down as they're making their way around their star?
They are, and that causes that. If you think of like an average, if there was no interactions, the average would be 10 days plus or minus 0.0000, and instead that uncertainty it grows by minutes and sometimes hours. And in an individual level, it's 10 minutes early or it's 10 minutes late, and it actually does change the orbital period.
I'm imagining 6 different little leap years.
Yeah, kind of, right? Have you learned how to keep your calendar straight?
I'm wondering, like, in these sort of situations. So you've mentioned the TTVs, the transit timing variation, the transit method, and the radial velocity method, right? When the spectral lines are shifting. Going beyond maybe stuff that you've worked on directly, I assume, from exoplanets to exomoons. Is there one of these methods that you think would be kind of have the best chance of detecting an exomoon?
Oh yeah, I mean, people love the idea of exomoons. So there's a lot of papers on it, and there's a lot of discussion and articles about it. One of the really good ways to do it is one of the methods that you mentioned, which is transit timing variations, and it's due to the moon then pulling the planet a little bit early or a little bit late. We have found moon type planets around like brown dwarfs. So that's something that's done with direct imaging, which we haven't talked about yet. That's sort of like the next hope for really learning a lot about small planets. Like, so the next really big, really, really high reaching goal for NASA is the Habitable Worlds Observatory. And that's supposed to launch in 20 or 30 years from now. And the idea is to directly image planets that are kind of basically like the Earth, like as close to the Earth as possible. Jupiter, sure, that's fun, and that's no big deal. And Neptune, that's great too. But like, the goal of that is to take a picture of a planet like the Earth around a star like the Sun. And for exomoons, it's a very good way to do that too. Like, you can potentially image things if they're really, really close. Yeah, exomoons are fun. They're just a really fun thing.
How similar to an Earth-like world how close have we gotten to finding something? I know we haven't found exactly an Earth yet. So far as we know, this is the only place that makes tacos, but how close have we found something similar in distance, size, I don't know, maybe possibly atmosphere, temperature?
Yeah, interesting. That's interesting, because every one of those things that you mentioned, there's sort of a planet that's really quite similar. So if you think of how a planet like the Earth is a certain distance away from the Sun, 1 astronomical unit, and we know about a lot of planets that are out there. And the ones that we do know about are more like Jupiter planets. They're like Pandora from the movies, right?
Avatar.
That's like the ones that are sort of at the right distance, the same distance as the Earth. For those that are the same size or similar in size, those are always much, much closer toward their star than the Earth is. So maybe orbital period of a few days, like Kepler-10. Much too hot to have water. Right, they're going to be sort of molten worlds full of lava all over their surfaces, evaporating the rock straight away from their surfaces into the sky, sublimating the rock.
Wow.
So so we have the size of planets, those are really close. The temperature that are further away. We even have systems where there's Jupiter-like planets that are like at Jupiter-like distances, and we're going to look really hard at finding planets that are sort of around Earth. Because some theories of planet formation say you need that Jupiter-like planet out there to sort of save Earth from any kind of incoming objects, comets and asteroids and things. Right? Jupiter clears out a lot of the debris, the planetary debris, leaving Earth in sort of a pristine environment to have longevity and not just get clobbered by comets like the dinosaurs did every few years. So let's see. So size, mentioned, distance away, temperature. People get excited about the temperate ones. There's some Neptune-sized planets that are about the right temperature. For temperature, what we do, because it's harder to find planets that are further away from their sun, when we try to find planets with the right temperature, we look around stars that are much smaller than the sun, much fainter and much cooler. Those things are all correlated for stars. And so a star like the sun, with like say some planet like the Earth, if it was going to have water on it, it'd have to be about an AU away. If you suddenly make the star much smaller, like an M dwarf or a red dwarf, you bring that distance much closer in. So now the orbital period's not 1 year, but maybe it's 10 days, like Proxima Centauri, one of the 3 stars in the Alpha Centauri system. So those, in that sense, we do have some measurements of the atmospheres of the planets that are maybe a few times larger than the Earth, are at that temperature, but they're much closer in because they're around those cooler stars.
I'm curious, you mentioned Proxima Centauri, and I know that there's been a lot of work done at radio wavelengths and other wavelengths to study that system and potentially for habitability. Not that you'd want to live on a planet that's constantly getting zapped by radio flares, but how much does your work involve multi-wavelength analyses, like looking at what other telescopes are finding on the sources of interest that you're looking at?
Yeah, the one that you mentioned is one that overlaps with my work sometimes. So if you think of the intense radiation that can happen, so maybe not radio, but like go to the other end of the spectrum, ultraviolet, UV and X-ray. When planets are forming, stars tend to have a lot more of that high energy radiation, X-rays and UV radiation. And people who study planet formation are worried that those early times in a planet's life, if a planet does have water, say it's like the Earth, it has some water on it, these stars are so vibrant and so active at these high energy levels that they just evaporate all the water off the planets. So people study that with UV and X-ray telescopes. But the tricky part is, if you want to understand the lifetime of a star, those lifetimes are so long that they have to study different systems that are young. Compare that to a system that's young with a planet, or older that's with a planet, and try to tie those things together in a disparate way. And that can be challenging because it's challenging to observe because a lot of times those signals are faint. It's challenging to interpret because people have different theories about how long those eras last for a star to have lots of radiation, and you can have really good interplay between theorists and observers, and we can make a lot of progress that way. But sometimes interpretation comes down to really small differences between particular theories. You have to have either an ozone or a protective atmospheric layers to sort of have life, and that's what we want to look for, right? Life.
Yeah, it's interesting. I feel like I've heard some suggestions that advances in evolution on Earth may have been sparked by these sorts of early time flares, but it's kind of you need just the right level. It's almost like a superhero origin story. You need the right level of intense UV or X-ray radiation to encourage life on an exoplanet or on a planet like Earth, but not too much that would just totally strip away the atmosphere or evaporate the water. Getting just right.
No, exactly right. And it depends on timing too, right? It seems like it might be okay at early times in a star's and planet's life. You really get that evolution going. And so some stars that have lots of that radiation are hotter stars, but then they also have, it's twofold. They have that more intense radiation at the start of their life, but their lifespan of that star, because they're more massive, is shorter. So maybe you have to have, if you do have life on them, it has to have that high energy radiation, really moving evolution quickly to get to that point. Whereas maybe it's a slow burn for the cooler stars. They have much longer lifetimes, 10, 100,000 times longer than those more massive stars. Maybe you don't need that radiation then to spark that because you have enough time for evolution to happen slower. Speculative, but I think fun to think about.
There's so many little sweet spots you have to hit.
But I mean, this is the problem when you look at brown dwarfs or ultra cool dwarfs. They live for so much longer, but a lot of them tend to be quite flary and quite volatile. So getting the worst of both worlds, or best of one, worst of the other.
Yeah, and of course that comes into play when you think about which kinds of targets we want to go after. So as we started the conversation today, proximity is a really important part of this, right? Things that are close to the Earth are bright, they're easy to observe. We're more likely to learn to measure them in multiple wavelengths, to know more about them in general. And then you compare that to these other questions about like, okay, well, does longevity of a system, is that important? Is the total X-ray luminosity important? And these are questions that were raised a lot when I was working for a program called Breakthrough Listen, which is a SETI project that's ongoing here at UC Berkeley and also at Oxford in England. And this was a really fun project I worked on for many years, where we did all different kinds of observations, and I would call it an intense observational campaign to look for signs not of life that come from like the oxygen in an atmosphere or the CO2 caused from industry in the atmosphere of some exoplanet, but instead we're looking for signs of technology, so coined technosignatures. And those would be things like radio waves that came from, the equivalent of our radio antenna, or satellites, radar, things like that. Or an optical, we have optical lasers on Earth. You can imagine that was used for communication by some extraterrestrial intelligence. And that was a fun project because these types of questions that you just brought up about proximity, longevity, intensity of radiation are all part of that discussion of like where you point the telescope, what are the best targets, where are the going to most likely find success.
Cool.
I'm just imagining people having like seriously heated conversations over where to point the instruments. Each of them convinced that they have the better subject to study.
Yeah.
Well, I was just going to say, like, we had a previous guest, Shanoa Tremblay, who was talking about installing these pipelines that run in the background on other observations that are just kind of like pointing everywhere. And these pipelines are not touching the science that the scientists are looking at, but just looking in the background for these technosignatures. That way you don't have to worry about where you're pointing. You'll cover, hopefully, everything.
Yeah. Oh, Shanoa was great. That's really cool. She was on here. These simultaneous measurements is especially easy with radio telescopes because you can divide the data feed into multiple places and do analysis in different timescales and things. And one of the really amazing things about Breakthrough Listen was that was one of it's definitely the biggest, not the first, but definitely the biggest effort to collect primary data for SETI instead of having to use the sort of secondary, wherever the telescope's pointing kind of philosophy. We could, for the first time, say, let's point here for an hour, then let's point over there for an hour. Let's go down this list that we just made with the closest, most nearby stars. Let's pick some sun-like stars. Let's pick some stars that are really old. Let's pick some stars that have lots of UV. And we did that, and we collected this list, going through this exact conversation that we've been having, and said, let's just point everywhere that we think is worthwhile. Going through all these different theories about where life might exist and how technology might be developed. And with Breakthrough Listen, both in optical and radio, we just did this massive campaign, still ongoing, looking for intelligent life in the universe. It was tons of fun.
When you say pointing here for an hour, there for an hour, is an hour enough time to, if you're focused on one spot, enough time to get possibly a signature of some kind, or do you need to like focus it for a day, a week, a year? Because it seems like not a lot.
Yeah, it's a trade-off, right? So if you think if you're looking for something that is common, then it's okay to take more time to point at one source at a time. If you're looking for something that you might not, you're sort of searching for it, you're not sure if it exists at all. Our strategy was to look at more things rather than fewer. And the trade-off of time versus sensitivity is part of the conversation. So it's sort of your question, I think, is maybe two parts. Do you make a sensitive enough measurement in an hour, and then are you looking long enough for something to actually be emitted in our direction? And both things are important. We came up with, I think it was actually 30 minutes, a 30-minute cadence, and that allowed us to do sort of our primary target list within the first few years, which was our scope for when we started. It's always a trade-off, though, always a balance.
Yeah, so cool.
Yeah. I had a really fun, one of the funnest papers I did one of the coolest projects I did was with a student who, at the time, she was a high school student, and I get lots of emails from people, and they're like, I want to come do research with you, and I'm like, great, and I'll send them something, and I never hear from them again. But this gal was really smart. So she was really smart, really self-motivated high school student. And I sent her some things to do, and she sent something back right away. And I was like, okay, great. Okay, here's something more. Like, give her something a little harder to do. And eventually, there was enough back and forth that this project was kind of coming together. Her name is Riley Derrick. She went to UCLA after being a high school student, and ended up publishing this paper, sort of just all in the background of all the other things that she was working on as a student. And it was kind of a cool project. It goes to this question of where do you point the telescope? And if you can imagine that over all the decades we've had space travel, we've been putting out things like the Voyager probe, the Pioneer probes, Galileo and Cassini, and they cover these really specific paths across the sky that are really well documented. And when we want to talk to them, or we want to download the data, we send pulses of radio data to them to communicate, and some pulses come back. But not everything gets absorbed. Not all of that signal gets absorbed. Some of it just goes right past Voyager or Cassini, and on and on and on out into space, out into the nothing of the cosmos. And so what we did is we used the Gaia catalog, the Gaia Space Telescope catalog we mentioned earlier, and we figured out exactly what stars would be in the background of those transmissions.
Like in the line of sight. Okay.
In the line of sight, and we had to take into account the motions of the stars because they're going to move in and out of that path. And Riley did all of this with the Gaia Space Telescope open public source data, and we tracked down all the JPL ephemeris. The Jet Propulsion Laboratory keeps track of where those telescopes were over time, and we did all the math in reverse and all the angles and everything. It was great. And it was funny because it was for me like sort of a side project with a student who was not even at the university, but it got more press coverage than anything I've ever worked on. People just loved the idea.
That's fantastic.
So yeah,
That's so cool.
That's absolutely fantastic. Who'd have thunk? Let's just draw a line from Earth through Voyager and just see where that line points over time.
Yeah. And then we made a prediction. So, you can make a prediction like if those stars that are in the background of those satellites were to receive our transmission that left in 1984 or whatever, how long would it take for the transmissions to get all the way there and to come all the way back? And so we made some predictions for 2034, we might see something from ET in that direction,
You might see a little signal that says turn the camera.
go away.
Go.
I know that Benjamin had. Yeah, no. I know that Benjamin really wanted to ask this question.
Well, I was going to ask about black holes.
Yeah. What do you want to know?
How many of them are named Kevin? I don't know. At least one. I was going to ask, what is the smallest or weirdest possibly black hole candidate you've seen or worked with?
The smallest candidates, yeah, that's a good one. So
I assume they're all weird because they're black holes, but
oh yeah, absolutely. So some of the classes of black holes include the supermassive black hole at the center of the Milky Way, a million times the mass of the sun. We think these are pretty common to the center of galaxies. The Nobel Prize was just awarded for this discovery a few years ago to Andrea Ghez and a few other people. More enticing are these for some people, are these sort of black holes that are about the same size as the sun, the same mass as the sun. So they come from stars that are maybe 10 solar masses, 10 times the mass of the sun. That star ends its life, it explodes in a supernova, and the remnant, what's left over, is a black hole. These are they are easier to find if there are two stars in the system and the black hole is going around a star that does give off light. So a binary star system, one component's a star, one component's a black hole. This is where some of the most recent discoveries have come. There's 3 that were just found called Gaia Black Hole 1, 2, and 3. These were found using Gaia astrometry combined with ground-based observing. So that's exactly what I've been talking about the whole time. You launch a spacecraft, it finds this amazing stuff. You use ground-based resources and telescopes to observe those same things, adding additional multi-wavelength data or spectroscopy or classification. And so these 3 systems were all Gaia candidates. We followed up from the ground, and they're all stellar mass black holes. What's really cool about these is they're in the stellar neighborhood. That same question from earlier about what's considered close. They're within, I think, 500 parsecs, 500 light years roughly, and that's cool because the numbers go, if you find these that are really close, that sort of gives you hope that their absolute numbers are much larger, because if they're super, super rare, the likelihood of them being near the Earth is small. So if they're close to the Earth, that's hopeful that there's a lot more of them. So these Gaia black hole 1, 2, and 3 discoveries were pretty neat. There's a former graduate student from UC Berkeley here, who's now a professor down at the California Institute of Technology, Caltech. His name is Kareem El-Badri, and he was the leader of these discoveries. Before that, he had been really good at publishing papers that killed black holes, right? Someone makes a black hole discovery, and he'll follow it up and be like, no. And he'll prove that it's some other astrophysical phenomenon. And so for these discoveries and some other work, all the other work he's been doing, he was just awarded a MacArthur Genius Award, which was pretty cool. And so you're in good company with your fascination of black holes. People are winning awards for this stuff.
Incredible.
Yeah. And the next chapter of black hole discovery is going to be pretty fun. One way to do it, aside from doing it with Gaia or looking at the centers of galaxies, is to use microlensing. So we watch different patches of stars over the course of time. We look for scenarios where the star gets a lot brighter, and that's coming from the magnification of one star over another due to their chance alignment. And when the lens, the thing doing the magnifying, is a black hole, it's a very specific signature in the light curve. And we've so far found one of these black holes. But there's a lot of hope for this, because next September 2026, NASA's Roman Space Telescope is going to launch, and it's going to just look at hundreds of millions of stars all at the same time, right toward the center of the Milky Way, the galactic bulge, and it's going to search for these microlensing events. And the hope is that it's going to find, dozens, if not hundreds, of these stellar mass black holes, as well as a gazillion other fun things.
So cool.
Silly question I've often had or wondered about black holes. If we had the smallest black hole collide, this is very stupid, with the biggest star, who would win? Would the star consume the black hole, or would the black hole consume the star?
Yeah, that's a good question.
Will the black hole just get bigger and bigger and bigger and bigger because it's eating it? Or would the star, which is like what? Is UI Scooty, would it just be so big enough it could rip apart like a stellar mass black hole?
Yeah, you might think that you're like in some like really crazy thought out here that no one's ever thought of, but there was totally a paper about this like 6 months ago.
I believe that there was.
And it was like, what would happen if these black holes are actually inside the sun? And I was like, this is a crazy idea. And like, here we are, talking about it. And I think that the answer was you would see signatures of this if they occurred. And because they sort of predicted like what the visible signature would be if black holes were in the sun or in other stars, and we would have seen that. And so it was like sort of saying that, we don't think that these little black holes would swallow up stars.
But even if there's like a massive size and mass difference, like something that's 1,700 times bigger than the sun and a black hole that's the size of the sun, it'll be a no contest.
Oh, well, if it's like a stellar mass black hole and another star, this is a scenario that we do know about. And what happens is we know about them because as they get closer and closer, some of the material from the star gets accreted or gets sucked up by the black hole. That gives off X-rays, and we can measure those. In the energy signature, you can figure out like that if it's a black hole or if it's another star. And so in that case, absolutely, that's exactly what happens. Before they even sort of approach each other, they start to spin around each other. The star gets eaten by the outside in, not from the inside out, but from the outside in. Eventually, just consuming all of that. What typically happens then is that you get so much mass that gets accreted from one to the other. Is you get like these huge flares and huge explosions. If it's actually a white dwarf that does the accretion, that pulls the material off of the other star, you can actually get a supernova that results in a black hole. And so it's sort of both ends of it. They can be the end result, or they can be the primordial nature. Yeah.
Crazy. Love it.
Yeah. Black holes are
Love
great.
it.
I try to keep I call it the highlight reel of astronomy. It's like I want to do exoplanets, I want to do black holes, I want to do life in the universe. It's like the stuff that people really want to talk about at the bar, like cosmology,
All the
I guess,
interesting
is
stuff.
Funny, when I want
Mm.
to talk about that kind of stuff at the bar, people just want to talk about football or something. And lame. So you need to tell me where the astronomy bars are. I'll go there.
I mean, that would be Jupiter's Pizza is the closest one that I can think of, right?
That's right.
Yeah, Jupiter, just down the street. Yeah, yeah. You had the Quasar, right? The Quasar beer down there.
I had it the first time I went, and then when I went back with Benjamin a few months ago, they didn't have it on tap. I was devastated.
Yeah, great spot, Jupiter.
Yeah. This is
All right. The closing section of every episode, we do a little rapid fire round called Questions and Quibbles. So we've got short questions. There'll be a nice mix of serious and silly. Are you ready?
We have serious
Ready.
questions. Yes, we
All right. First question. What is the weirdest thing that you believed as a kid?
Weirdest thing I believed as a kid. I mean, I don't know. Probably, I thought of Santa Claus first. Like that's pretty normal, not that weird. Yeah, I think that I was sure that I was going to go to Mars. I was like, that was like, that was an obvious thing to me. Yeah, Mars. I'll go there. Sure.
Nice.
No big deal. Yeah.
Maybe you will.
Maybe it's not too late.
I don't think so. Which teacher had the biggest positive impact on you?
Easy one. This is Mr. Magnuson. He was my 8th grade science teacher. He introduced me to space science, basically the Galileo space probe, which was just going to Jupiter at the time. I got to take time out of my other classes to work on this project using the World Wide Web, which one computer in the whole school had that back then. There was no exoplanets at that time, so I wasn't yet into that, but just sort of being motivated to, enlarge my sense of discovery. We looked through a telescope to look at the rings of Saturn, which is a really common origin story for astronomers. Mr. Magnuson was definitely a really big influence in my life when I was young.
It's awesome.
Nice. What's one scientific discovery you wish you could have witnessed in person?
Ooh. Well, I've witnessed some pretty good ones. Let's see. Do you mean to go back? Can I go back in time to do this, or?
Yeah, anything you
Yes.
want.
Time travel is allowed.
Yeah,
Time
I mean, I
travel
think
is
so. Like the things that I think are just totally incredible are sort of big names, like figuring out that we weren't at the center of the solar system. So like Galileo looking at the craters of the moon or the moons of Jupiter or the phases of Venus, like those things combined showed that the Earth is going around the sun rather than the other way around. That's the kind of thing, like you say it and you're like, sure. Okay, but maybe not. But so that's a really good one. I think that one's really good because that's pretty important discovery. But I'll do a second follow up, which is electricity. Because if you read about the accounts of people seeing electricity for the first time, even educated people, it was basically magic. And so that would have been amazing to see, not know about that and then be like, oh wow, this is electricity. This is amazing.
Oh, good answers. I like these.
That's a good one. All right. If you had to pick one historical scientist to go bowling with, who would it be?
So a little bit more of a hang session, bowling with the scientist. Yeah. That's a good one. Let's see. I don't want to go back too far. Maybe a little bit more modern one. Let's see. Maybe Hubble. Yeah. Old man Hubble. Because it was in LA. They probably even had bowling alleys back then. I don't know how well bowling is, but there probably would have been a really cool Big Lebowski kind of bowling alley that we could have gone to. Right? That's just outside Pasadena. I think you guys were talking about Mount Wilson Observatory a few episodes ago, and he would probably live down the street from that same bowling alley or something. That would have been a blast.
I could see that. I could see him having a personalized. Yeah. All right, a serious question now. If you were a sandwich, what kind of sandwich would you be?
Oh man, For people who know me, this is a really funny question because I absolutely love sandwiches. Okay, so I'm not saying it's like the absolute best sandwich, but like a really solid sandwich starts with homemade bread. I do a little bit of bacon. I always have homemade bread in the house, sourdough, spicy mustard, and butter on the other side. I'm only just getting into mayonnaise now, so I'm sticking with butter for now. Turkey and ham, pepperoncinis, Tillamook sharp cheddar. And the key is you can't just like eat it right away. You have to put it in the sandwich bag and like, carry it to work or like do your hike or whatever and eat it several hours later. So it's got this nice maturing time in the
Nice
bag.
maturing thing. Not just that, but the anticipation time also.
Yeah.
It's just hitting me that every time we've asked this question, the answer to the question of what kind of sandwich would you be has always been what kind of sandwich would you eat?
Oh, would I be? Is that what it was? Is that what the question was?
No, it's fine, but like you answered it the way that everybody else answers it. I've just realized that we've been asking that question for dozens of episodes, and everybody answers it exactly the way that you do.
So I guess you'd want to be your favorite sandwich then is the answer.
I think so. I think that's the takeaway message.
Okay, next question, and this is like the hot question of our series. What is your most controversial opinion about pizza?
Let's see. Okay, that's not controversial. Not controversial. I will say that that Domino's pizza is excellent.
Good one. Nice.
This episode is not sponsored by Domino's Pizza.
No, Domino's pizza is great. It's like it's the same every time. The crust is really good. Like it's not too expensive. It's super solid. We go Domino's.
What were the two things that you were saying to yourself and not controversial? I'm curious.
Oh, I was gonna say, well, pineapple doesn't belong on pizza. I think that's a big split position. Not too controversial. Not a minority, but definitely people take sides on that one. And, it's probably up there with like whether or not cheese belongs in the crust. I don't know if it does or not, but people feel pretty strongly about this cheese in the crust business. Like, wrapped inside the crust.
I've never cared for that. I've seen it made, and it's kind of fascinating to see how like people who really take pride in making a cheese-filled crust make it. It's kind of cute, but it's just not for me. That's just too much.
See?
It's that Jeff Goldblum line from Jurassic Park, right? Like your scientists or your chefs spent so long trying to figure out whether or not they could put cheese in the crust that they never stopped to ask themselves whether they should.
Would you like some pizza with your pizza? I got you a pizza with a pizza built in.
I just love homemade pizza. Though we have an uni grill, not sponsored by Uni. Those are pretty good. I recommend them.
Yeah, those are nice. Nice. All right. What is your favorite scientific word or phrase?
Ooh. Or phrase. Periastron passage. It's pretty good.
Ooh, that's a good.
Periastron passage.
Do you want to?
So when you have
that one.
It could be planets or stars, but the easier scenario is you have a planet going around a star. It's on an eccentric orbit, so not circular like the Earth's, but eccentric, meaning it has different points in its orbit. It's further or closer away from its star. It's an ellipse or an oval, not a circle. And when it's closest to its star, the very closest point is called periastron passage. And it's used to define like the angles of the orbit and the semi-major axis. And it's sort of a fundamental way to think about the mathematical definition of an orbit, periastron passage. And what was it? Was there a second part to that? Or just one phrase?
The second part is the next question. What is your least favorite scientific word or phrase?
That's funny. There's a couple that I can think of. One of them, so when we started making discoveries with the Kepler Space Telescope around 2009 and 2010, it was a NASA mission which required a dictionary full of acronyms, and NASA just loves acronyms, loves. That was the first paperwork I got, was the acronym book. I'm like, okay, you guys are serious about acronyms. And Kepler Objects of Interest, KOIs was like, that's your standard planet candidate before it becomes a planet or before it's identified as a false positive. And someone really wanted to name these KOIs. And I just thought that was like the worst word ever. Like, we're this really awesome KOI. We know what it means. We're excited. We're going to find planets. Just don't call them KOIs. That's not a good word.
It would have been great. You'd have the Kepler and the TESS objects of interest. You'd have KOIs and toys.
No, boo. Terrible.
All right. What is your favorite useless science fact?
Oh, I mean, geez, you're talking to someone who has absolute million useless science facts. I mean, I've probably said a bunch of them here. Stars are within 100 parsecs, things like that. So let's see, useless science facts. I got a lot of useless geography facts. Useless.
Sure.
I mean,
Geography is a science.
Anything.
I was thinking of useless science facts. I mean, first of all, science facts can't be useless because they're science. How about that? I don't know. Nice. I throw things around at people all the time, and sometimes they get a laugh, and sometimes they're like, that doesn't make any sense. Like, people love to hear about the number of planets there are out there. If we found, how many black holes, or, where the nearest planet, like the Earth is. Yeah, I don't know. I love my science facts too much, I guess, to think of one that's truly useless.
They're all useful.
Bad answer.
Okay. If you could rename one planet in our solar system, what would you call it?
What would I call it?
Yeah.
It doesn't matter which one.
Which planet needs a new name, and what should it be?
Well, any planet that needs a new name should definitely be Planet Howard. I mean, pretty obviously, because so an exoplanet, like if you discover a comet, you get to name the comet. If you discover an asteroid, you get to name the asteroid. So people would always be asking me, like, well, did you discover any planets? And I'd be like, yeah. And like, did you name it after yourself? I'm like, no, that's a good idea. And then once in a while, you get someone like, they'd be like, oh, well, did you find new planets? And I'd be like, yeah. And they'd be like, can you name it after me? So there's a lot of requests to get planets named after people.
Okay.
But yeah, right here.
All right, final question. It's a big one. If you had to sing one karaoke song to save humanity from an alien invasion, what would it be?
Well, that's really funny. Okay, I'm going to be honest here and say that I'm not going to pick like my favorite song, which would be different than this. But my wife always jokes that it would be TLC's Waterfalls.
Don't go chasing them.
And if it would only be if we needed to save humanity, because no one would want to hear that otherwise.
You're saying the aliens would just hate it so much that they would.
Yeah. Pass. Next planet over. That's a funny one, though.
Hey, as long as you're saving humanity, that's all that matters.
That's all that matters. That's all that matters. Right. Job done. Job done.
That's right.
Nice. Howard, thank you so much for joining us and for answering our questions and putting up with our shenanigans.
Happy to do it. That was a lot of fun. Thank you for having me.
Oh, dude, thank you.
If people want to find you online or learn more about your research or the work you do, where should folks look, or how can they get in touch with you?
Yeah, thanks for asking that. I don't have too much on the socials, but I think some really amazing places to keep an eye out for astronomy news are the Keck Observatory press releases. Keck Observatory in Hawaii is one of the most prolific and amazing telescopes in the world. The people in the community that are involved at every level of that are the most amazing people I've ever worked with. So keep an eye out for things there. And things like Astronomy Picture of the Day, NASA press releases, they're going to hit all the highlights. Just, NASA
Those are
and
great.
Keck Observatory. Those are highlight those.
Nice.
Nice.
Benjamin, what about yourself? Where can people find you if you want to remind our listeners and viewers?
As always, look up Science Actually on your favorite social media platform or some of the other ones. I'm there too, probably. Look for Science Actually. Get your daily science facts and collective nouns and science articles. And you can also go to YouTube and TikTok and watch this show, or go to your favorite podcast provider and listen to this show. How about you, Kavi? Where are you?
Folks can find me at Fun Fact Science on all good social media platforms as well as the bad ones. Feel free to take a listen or watch to any of our old episodes. Let us know what topics or guests you want to see in future episodes. And we will see you next time on the next episode of Science Actually Presents the Nerd and the Scientist.
Later, all. Thank you, Howard. Thank you, Kavi. Peace.